Hi, welcome to Algebra 2 Common Core. In this last lesson in our unit about trigonometry, we're going to look at simplifying all of the trig expressions that we've been working with throughout this entire unit. So let's start with our basic identities and let's fill them into the boxes at the top of your page so that we can keep referring back to them. So for the Pythagorean identities, we know that that is going to be cosine squared theta plus sine squared theta is equal to 1. Now again, I don't memorize the other two, I just know how to get the other two from this one. So for example, if I go ahead and I divide each and every term by cosine squared divided by cosine squared is 1. Sine squared divided by cosine squared, we should know by now that that's going to be tangent squared of theta. And 1 divided by cosine squared, that's going to be secant squared of theta. Now let's go back to our original Pythagorean identity and now divide everything by sine squared. Cosine squared divided by sine squared, that's cotangent squared. Sine squared divided by sine squared, that's 1. 1 divided by sine squared, that's cosecant squared of theta. So we get the three Pythagorean identities that will be useful for us in simplifying trig expressions. In the next box, let's write down our reciprocal identities. So our definitions for the reciprocal functions, the secant of theta is just the reciprocal of cosine, so 1 divided by cosine. The cosecant of theta, that's the reciprocal of sine, so cosecant is 1 divided by the sine of theta. And the cotangent of theta is the reciprocal of tangent, so that's going to be 1 over tangent of theta. Now technically all of these are reciprocals of each other, so for example tangent is also equal to 1 over cotangent. Sine is also equal to 1 over cosecant, and cosine is also equal to 1 over secant. The quotient identities are the trig functions that are created by doing a division. So we know those to be tangent of theta is equal to sine of theta divided by cosine of theta. And the reciprocal of tangent is cotangent, so that would be the reciprocal cosine of theta over sine theta. So these will be our 8 most important trig expressions, or trig identities, so that we can simplify all other trig expressions. So keep these at the top of your page and we're going to keep referring back to them. So number 1 says, let's simplify each of these expressions. I see 1 minus cosine squared, so I am just going to refer back to my Pythagorean identity. Remember that cosine squared theta plus sine squared theta is equal to 1. So if I go ahead and I subtract cosine squared from both sides, I get that sine squared of theta is equal to 1 minus cosine squared of theta. So I can replace my original 1 minus cosine squared of theta with what it's equal to. The identity here would be that it's equal to sine squared of theta. So I can replace 1 minus cosine squared with sine squared. In number 2, I've got sine times cosecant. Whenever I see one of the basic trig functions like sine or cosine, I leave it as is. But then I'm going to replace the cosecant with what that's equal to as a reciprocal. So cosecant is 1 divided by sine of theta. Do you notice that we can cross cancel sine of theta with sine of theta? So therefore, this is all equal to 1. So anytime I'm multiplying a function by its reciprocal, the answer is going to be 1. I see something very similar in 3. I'm going to write tangent as sine divided by cosine. I'm going to write cotangent as cosine divided by sine. And again, I'm referring to those identities that we wrote in the boxes above. Cross canceling, cosine divided by cosine gives me a 1. Sine divided by sine gives me a 1. So this product is 1, and again I see that property that when I multiply a trig function by its reciprocal, I always am going to get the answer of 1. So tangent times cotangent is 1. There's also a few other ways that I could have approached that problem. I could have also said cotangent is 1 over tangent, and then the tangents would have cross-canceled. Now in the next example, number 4, again I'm going to go back to my basic trig functions. So I'm going to write tangent as sine of theta over cosine of theta. And I'm going to say cosecant is 1 over sine of theta. That will allow me to say sine divided by sine just gives me a 1. So when I multiply the numerators, I get 1. Multiplying the denominators, I get cosine of theta. But we all know that 1 over cosine of theta is just equal to the secant of theta. So that tells me that this product is equal to secant of theta. So very often in trigonometry, it's going to be helpful for us to be able to rewrite trig expressions in a different form, as we have done in these first 4 examples. We'll see that the next 4 are a little bit more complicated, but we're going to still follow the same approach. For number 5, I've got cosine, and cosine is one of my basic trig functions, so I'm going to leave that as cosine. It might even be helpful to write it as cosine over 1. Tangent, of course, is sine divided by cosine. Cosecant, that's equal to 1 over sine of theta. Oops, I should have said times there, not equals. Let's get rid of that equals. So 1 over sine of theta. And then sine squared is really just sine of theta times sine of theta. And that would all be over 1. Now let's go ahead and do any cancellation that can happen. In this case, I can cancel a cosine with a cosine and get a 1. I can cancel a sine with a sine, and it doesn't matter which pair of sines I canceled as long as one was in the numerator and the other in the denominator. So left over in the numerator, I have 1 times 1 times 1 times sine, so that's going to be a sine squared of theta. And in the denominator, I've canceled everything except for the 1's. So my final answer for this one in simplified form is sine squared of theta. So you'll notice that I took 4 trig functions and multiplying them all together, I got it down to just a sine squared of theta. For number 6, I've got a division. So let's see how we're going to approach division. Cosecant of theta is going to be 1 over the sine of theta. And then I'm dividing by secant, which is 1 over cosine of theta. Now when I divide with fractions, I'm going to keep the numerator. I'm going to change to multiply and multiply by the reciprocal of the denominator. So I'm going to have 1 over cosine times cosine over 1. Now multiplying the numerators, I get cosine of theta in the numerator. Denominator, sine of theta. Do we all recognize that that's just equal to cotangent of theta? So this quotient simplifies to the function cotangent of theta. Let's go ahead to number 7 where I've got multiplication and division. So tangent is going to be sine theta divided by cosine of theta. But I'm multiplying in the numerator by cosine over 1. And then eventually I'll divide by sine of theta. So first of all, I see that I can cancel off my cosines. So in the numerator, I now just have sine of theta over 1, which is sine of theta. In the denominator, I have sine of theta. So sine of theta divided by sine of theta is just equal to 1. So this whole big complicated expression really always has a value of 1 regardless of what the angle is. Let's finish it off with number 8, which is a little bit different here. I see that I've got the binomial sine theta plus cosine theta, and we want to square that sum. So we're going to expand this by saying sine of theta plus cosine of theta times sine of theta plus cosine of theta. So I'm going to do a double distribution. So sine of theta times sine of theta. You can even mark what you're multiplying together here. That's going to be equal to sine squared of theta. Then I want to multiply the sine of theta times the cosine of theta, so that'll be plus sine theta cosine theta. I'm just going to color code my products here. So then I'll multiply the cosine times the sine, and it doesn't matter what order I write that in, so I'm going to write that as sine theta cosine theta. And then let's multiply this cosine times this cosine, so that's going to be cosine squared of theta. Now you'll notice that the two in the middle are like terms, so I can add those two together and get 2 sine theta cosine theta. And I'm going to bring the other two next to each other because they look familiar. Sine squared theta plus cosine squared theta. And I'm still adding on the 2 sine theta cosine theta. Do you recognize the first two as our Pythagorean identity? So sine squared plus cosine squared is 1. So I've got 1 plus 2 sine theta cosine theta. So this is another way of writing that original expression by simplifying using our Pythagorean identities. Now in our last two exercises, we're going to take a different approach. On the front side of your notes, what we were doing was trying to find another way of writing each of those expressions. Anytime we did that, we created an identity because what we started with on the left side was always going to be equal to what we ended up with on the right side. In 9 and 10, it says, prove that the following is a trigonometric identity, beginning with the side of the equation that seems to be more complicated. Be sure that the complete identity statement is included at the end of the proof. So when I look at this expression, first of all, I've got tangent of x is equal to secant of x over cosecant of x. So we're going to work with the side that's more complicated. Now, please don't be thrown off by what this says over here. So never ever give up on a problem just because we've got something complicated written after it. All this means is it's telling me my domain. It's saying I can't have any 90-degree angles or any multiples of those 90-degree angles when I end up with odd multiples of pi over 2. Why can't I have that for x? Because that's going to make my cosecant of x be undefined. So therefore, I can't ever let x be equal to this value. I don't need to do anything with this statement. This statement is just like saying, just don't let x be this value. But I'm not going to do anything with that as I solve the identity problem. So I'm going to leave the left-hand side, the tangent of x. On the right-hand side, we're going to do what we did on the previous page. We're going to say secant is really 1 over cosine of x. Cosecant is really 1 over sine of x. And again, focusing on working on the more complicated side. Now, the left side is staying a tangent of x. And on the right side, when we have division of fractions, we're going to keep the first fraction, change to multiply by the reciprocal of the second fraction. And again, working on the right side of the equation, we end up with no cancellation, but instead we write sine of x over cosine of x. Do you recognize that sine of x over cosine of x is equal to tangent of x? So I see that the left side and the right side match, so that tells me that I have an identity. That tells me that no matter what value I put in for x, no matter what angle, as long as it's an angle in my domain, I will have the left side equaling the right side. These identities are super important in Algebra 2. We saw them with polynomials, and now we're also seeing them with trigonometric equations. Let's approach example number 10 in the same way. It says, prove that the following is a trigonometric identity. So again, I want to focus on the side that seems more complicated. This one, it might be a little harder to decide which one's more complicated. So I'm going to start on the left side and say, well, cotangent of x, that's going to be cosine of x over sine of x. Plus tangent of x, that's going to be sine of x over cosine of x. Let's let our right-hand side just ride for now. So secant of x times cosecant of x, and we'll see what comes out in the wash. Again, don't be intimidated by this statement. All it's doing is telling us what our domain is for these functions. Now on the left side, when I'm trying to add two fractions together, I know that I've got to have a common denominator. So the first fraction has a denominator of sine, the second fraction has a denominator of cosine. So I am going to make my common denominator be the product sine-cosine. So that tells me that my first fraction, I have to multiply the numerator and the denominator by cosine of x. So that my denominator will now be sine of x cosine of x. Likewise, with my second fraction, I'm going to have to multiply that fraction by sine of x in the numerator and the denominator, so that my common denominator will also be sine of x cosine of x. Now on the left side, when I multiply together cosine of x times cosine of x, that's just giving me cosine squared of x. On the right side, when I multiply the numerators together, sine of x times sine of x, that is also sine squared of x. Now, don't be tempted to do any cancellation, because if you do, we'll be back at the original problem. Instead, now that we have our common denominator, let's add together our numerators and put it over that common denominator. And you'll notice that the right side just stayed my secant x cosecant of x all the way down. I'm not changing it at all. I just want to see if I can get the left side and the right side to match each other. Now, did you notice anything on the left side that looks familiar? Should we replace that cosine squared plus sine squared? I know, of course, that that's the Pythagorean identity, so that's 1 over sine of x cosine of x. Do you see that we're ending up with this product secant times cosecant? It might be easier to see if we break apart the left side. So this would be the same thing as saying 1 over sine of x times 1 over cosine of x. 1 over sine of x, of course, is cosecant of x. 1 over cosine of x is, of course, secant of x. And I end up with the left side of my equation being exactly equivalent to the right side of my equation. So when I see that the two sides match, I say, yes, this is an identity, because the left side and the right side match for whatever value of x is in the domain. So we've seen some examples of simplifying trig expressions, and we've also seen some examples of working out identities to show that the left side and the right side of an equation equal each other. That's what an identity is, a statement that is always true for all values of x in the domain. Thanks for working on trig simplification tonight. Have a great day, and we'll see you next time. Bye-bye.